Hi, good afternoon, everybody. I'm Patel from Laboratory for Computational Sensing and Robotics at Johns Hopkins University. I'll be presenting our work on safety in retinal surgeries, bimanual robot-assisted retinal surgeries. This is a collaborative effort with Johns Hopkins and Hopkins Medical School. The agenda for my talk is that I'll talk about the retinal diseases and then what are the retinal surgeries that are performed to cure those diseases. And then I'll talk about why safety is important in bimanual operation. And I'll introduce the tools that we use for performing the surgeries, which includes a robotic device, force sensing tools, which are based on FPG. And then I'll talk about what are the experiments we did and what are the results we achieved. So some of the eye diseases here, as you can see, a normal vision actually is something where you don't have any blurred portion of the image, don't have any dark portion of the image, but certain retinal diseases cause either a part of the retina is basically destroyed in a way that you don't have very good image for the person who is seeing any object, and that's diabetic retinopathy. Then there are a few more diseases resulting in either blurred vision or kind of fog vision. Now, these retinal diseases are very difficult to actually cure, and over the time there has been a few retinal surgeries that are performed now routinely. So that includes laser photocoagulation, which basically removes any clotting that could be there, and then you have a couple of other procedures related to removing, if there is a membrane that has built up on top of retina, it has to be removed surgically. And we are talking about here size of membrane which is few micron thin, and you are dealing at the forces which are in range of few millinewtons. So the problem here is that the clinician does not really feel any of the forces. One of the procedures which is not yet a clinical procedure, an experimental procedure, is vein cannulation, which is you are trying to, if the vein is occluded because of clotting of the blood, you are trying to inject anticoagulant into a vein which is size 100 micron with a needle which is about 60 micron, while our hand tremor itself is about 100 micron. So it's a very, very challenging procedure. There are only very few clinicians in the world who can actually perform this procedure. And that is the reason that it's not yet a clinical practice. To perform these retinal surgeries, we use these really miniature tools, forceps or hook-like tools. So I'm going to talk about some of the tools that we have sensorized in order to sense the tool-tissue interaction. The retinal surgery, the challenges that you can see here, first of all, it's a bimanual operation. If you look here, the clinician is basically with a very limited availability of the space around the eyeball, manipulating two tools. One of them usually is a light pipe, which is to shine the light and look through the lens, and the other tool is actual tool to perform the surgical procedure. So if you look here, this is a constrained space, so both hands have to move together in order to limit the force that acts at the sclerotomy port. This is the white part of the eye, so they make two incisions, put trocar through which they insert these tools. And what we are trying to do over here is basically measure these forces. One of the challenge here is these forces are so small, they're non-perceivable. And we did some studies with actual clinicians and see that they start perceiving this force at the sclera at about 50 millinewtons, because they are so well trained. Their hands are so very well trained that they can perceive forces of 50 millinewtons. Below 50 millinewtons, they don't have any perception still. So that's the place where we can actually use force sensing tools. Retinal surface, that's even a different story there. You're looking at forces in range of about 7 to 10 millinewtons. There is no way they can perceive with the tool basically. So we have built tools which allow to measure those interaction forces. Because this is a very delicate surgical procedure, it requires really precise motions. And hand tremor itself is about 100 micron, resulting in basically if I'm trying to do a procedure which requires 50 micron accuracy, it's very unlikely that I would succeed every time. And the fatigue, because you see, it's not very ergonomic, there isn't really a lot of space for the clinician, so fatigue results in even a worsened condition as the surgery progresses. So over the last decade, there has been a development of good number of robotic assistants. They improve the precision, they reduce fatigue. And recently, these two systems have been actually used clinically. This happened in last 2 years. One system at University of Oxford and another at Eindhoven, and they have performed these two procedures, retinal vein cannulation and epiretinal membrane peeling. So what we are seeing here is that it is now becoming a possibility that we could have a robotic assistant for retinal surgeries. And what you are seeing on the right is a Johns Hopkins steady hand eye robot. This has been an ongoing project for about 10 years now. And it's a cooperatively controlled robot, which means the clinician and the robot are sharing the same tool. I'll talk about a little bit more about this robot. The focus of this paper is actually safety in bimanual operation. And what we are trying to do over here is we have a robot holding a force sensing tool and a freehand, which is also a force sensing tool. We are trying to measure both the interaction forces with the robot and the other freehand motions. We are trying to measure the interaction force at the sclerotomy for both of these tools. And we are trying to understand how could that actually impact the safety in the surgery. This is a very preliminary results. We have just set up this system to start collecting data and understand what is the correlation between the both hands and what are the actual forces, interaction forces. Now talking about the iRobot, or the steady hand iRobot, it has very high translational resolution, less than 3 microns. So if you see here, it has XYZ stage. On top of that, we have this elongated arm with 2 rotations. It has an RCM mechanism. That means there is a fixed point in space which does not move no matter what happens with the rotations. And then at the end of the effector, we have a 6-TOF force torque sensor, and that is where we attach the tool. And what happens is now with this control law, we are measuring the interaction force through the force torque sensor and feeding that back to the control system, which is generating the desired motions. So it's a hand-in-hand cooperative operation of the robot. The advantage of this is that clinician never loses control of the tool, which is very important in terms of safety. There are multiple approaches, either teleoperated or hand-in-hand, or if you can have autonomous. But here we are relying more on the clinician. We have a quick release mechanism, which means if something goes wrong, clinician can right away pull out the tool. The force sensing instruments, we have built various different kind of force sensing tools over the period of last few years. We have hoop tools, we have microforceps. In this study though, I'm going to talk about multipurpose force sensing tool, which can basically measure interaction force at the tip. It can measure the interaction force at the sclera and the insertion depth, how deep the tool is inserted into the eye. We are doing this with Retinal wire, which is 25 gauge, and on that Retinal wire, we have put 3 fibers at 120 degrees. This is the cross section of this tool, and then we have 3 fiber grating sensors per fiber, so total 9 FBGs, and we are measuring these quantities. And here I'm going to talk more about the sclera force only. This is the force sensing method that we are using, which is fairly simple. You can say that the change in the reflected wavelength from FPGs is directly proportional to the strain or force. You can convert strain into force with measurements. I wouldn't go into the math, but if you are interested, you can look up into the paper that we have. Now, to calibrate this tool, because this is a change in wavelength that we are trying to measure and convert it into force, what we are doing here is we have a robot holding the tool. We apply a known amount of force, measure the scale value here. So we are recording basically here all the 9 FBG values and the scale value, and building a 9 by 1000 readings for each of the force value. And then using this one now, what we are doing is doing the calibration, and that calibration results into 2 matrices basically relating the change in wavelength to the desired force values. And this is the validation result of the tool. And both the tools we used in this study, they have RMS error of 2.3 millinewton and 0.7 millinewton. You can see there is a variation here, and that depends on how we build the tools. So we are building these tools actually on our own. We can control the robot with these tools, and this is something we have kind of tried to explore more into using the force information. This is the experiment setup. Basically, as I said in the beginning, you have these force sensing tools, and we are trying to evaluate them for different tasks. We are trying to rotate the eyeball, or try to move both the tools closer to each other, or try to move around the retinal vessels, which are painted in the eyeball. So these are 5 tasks we evaluated. We performed this experiment, one clinician and one engineer, repeated those 5 tasks for 4 times, and 20 trials for freehand and 20 trials for robot assistance. And what we observed here is that for both the cases, in all conditions, the dominant hand, or which is held by the robot, exerts more force than the non-dominant hand. And one of the reasons could be that because dominant hand is the one which is actually initiating the manipulation. So it's always exerting more force, and the non-dominant hand or the free hand is following that motion. Also, we observed that the robot exerts more force than the free hand, and the reason would be that there is no perception of the interaction basically. When the robot comes between the actual tissue and this, the tool, there is no information about what is the interaction happening there. So we are working on that. How do we restore that? Also, we tried to look at the correlation between left and right hand, and we didn't really find any correlation. This is interesting because we thought there should be some correlation when you're doing bimanual operation, but this is preliminary data and we didn't find any correlation. So this is what I presented, FPG-based force sensing in retinal surgery for safety. In future, we would like to have bimanual operation and multi-user studies, perform ex vivo operations. This is the direction we are moving into. And I would like to acknowledge NIH funding. That's pretty much all. Thank you very much.